So good afternoon, everyone. Thank you for joining this session and inviting me here. So my talk today is about nanotribology on soft surfaces. I know that some of you might not agree with the term soft and prefer like a term like compliant. However, I think that that's a bit more interdisciplinary, so I will stick with that, although not exactly correct. So I will start with a bit no foundational knowledge about friction, covering distinctions between macro and nanoscale. Then we will explore a couple of case studies from my postdoctoral research area in the University of Leeds. So a bit about myself first. So I started my academic journey at the University of Crete in Greece, where I studied materials science and technology. Then I moved to the UK and I did my master's in nanomaterials for nanoengineering. I continued with a PhD in the University of Birmingham, where I studied interaction between proteins and biomaterials under the guidance of Professor Zeniu Zhang, as I guess most of you know. And then I undertook a postdoctoral research in the University of Leeds, working with Anves Sarkar and Simon Connell and studying lubrication, oral lubrication on the nanoscale. So last year I transitioned to industry and I'm working now as a researcher in Unilever, where I study tactile perception and skin tribology. So this slide, I wasn't sure if I would include it because I guess most of you know about friction. I will just go quickly over that. So friction, as all of you know probably, is a resistant encounter when an object moves relative to another object. And it's everywhere, from simple acts of walking and grabbing to writing, breaking, etc. So when we zoom into the nanoscale, what is different? So friction here finds applications, again, in various advanced technologies. For instance, microelectromechanical systems, such as accelerometer and gyroscopes, are commonplace in most smart devices today. And also, we can see nanofriction in biological systems, such as the gecko food. So getting a better understanding of friction at this very small scale will propel us forward and inspire innovations in fields such as biotechnology, communications, and medicine. So you might wonder why soft surfaces. Well, consider that the elastic modulus of biological systems, such as the eyes, oral cavity, and the joints, ranges from a few kilopascal to a few megapascal. So understanding friction in these systems and how soft tissue interact with biomaterials is pivotal for designing novel biomaterials that interact better with the human body, not only. So to dive a bit deeper into nanotribology, so nanotribology is about studying friction, wear, and lubrication, but on a much smaller scale, as you expect. So at this level, surface forces, and particularly adhesion and friction, become dominant. And that's mainly because the proportion of surface atoms, if you think of a small body, the surface atoms to the total atom of the total body increases as you go to smaller scale. And surface forces become more and more important. Given the small scales at which forces are measured, surface forces become very dominant. So friction behaves differently depending on the scale that we are looking at. At the macro scale, we have Amonton's law, firstly recorded by Da Vinci, which states that frictional force is independent of surface area and depends only on the normal load. Now, at this scale, even a flat surface seems very flat, but as you zoom down, you see that actually most of them, if not all of them, except some exceptions, become multi-asperity contacts and is composed of a plethora of very tiny peaks. And here friction may increase either linearly, as was the case in macro scale, or sublinearly, depending if there's adhesion there or not, most of the times. And finally, at the nanoscale, we encounter simple single asperity contacts where friction increases sublinearly with load and revealing a dependency on contact area. So let's discuss a bit about why this happens. Now, in multi-asperity contacts, friction is generally independent of the contact area. And that happens because the real contact area, which is a summation of all these small aspects that we discussed about, can be up to 10,000 times less than the apparent contact area, so what we see. So as the load increases, those very small asperities deform and the real contact area increases. So this results in balancing the contact pressure because it is distributed over a larger area, which results in this independency from the apparent contact area that we observe in the macro scale. Now, in contrast, at the nanoscale, when we encounter single asperity contacts, friction is much more dependent on the contact area. And then as the contact area increases with load, friction also rises correspondingly, as we will see in the next slide. So let's see a bit about contact mechanics to see how the contact area increases with different models. The Hertzian model is predominant at the macro scale, where adhesion is in most of the cases negligible. However, as we go down to smaller scales, adhesion becomes more and more important and significant, and we need a different model to calculate the contact area. And the most applicable models are JKR, most of the cases for tribology and soft surfaces. DMT also can be used. The difference between a big difference is that the JKR model, so the Hertz and DMT model predict a zero contact at the pull of force, so when you pull separate the two surfaces, as opposed to a finite contact area calculated by a JKR model. So JKR is mostly used for short range compliant materials, while DMT is mostly used for stiffer materials that you have longer adhesion, long range adhesion forces. Now, because the JKR and the DMT models calculating adhesion at the opposite ends of the same spectrum, we have also other models such as the Mao-Gies or the GT model that can calculate these extremes and also all the cases falling in between these cases. So the atomic force microscope is a valuable tool in that field. So the AFM operates by using a very small sharp tip that is attached to a cantilever. So its movement, both vertically and laterally, is detected by a photodetector when illuminated by a laser. So primarily, AFM is used for imaging purposes, as it can trace a surface area, surface and generate a 3D topographic image of that. But it also can be used to measure interactions between the tip and the surface, such as adhesion forces or friction forces. So in AFM, there is a diverse range of probes to choose from. So we have sharp AFM tips that are the go-to solution when we want to do high-resolution imaging. So these are typically silicon or silicon nitride. Although they can be functionalized, they can have different coatings, gold, etc., or put some molecules there and functionalize them. So on the other side, we have colloidal probes that are mostly employed for force measurements. We can attach various particles at the end of tipless cantilevers, and we can create probes that tailor the specific mechanical and chemical properties for our applications. So each type has its unique applications and advantages. So let's take a moment now to see how the friction force microscopy evolved. So friction force microscopy is based on AFM. So AFM was developed in 1986 by Binning et al. And was firstly used to measure lateral forces in 1987. And initially, it was used to study frictional phenomena at the atomic scale, such as stick slip, anisotropy, and superlubricity, using sharp tips. Colloidal probes were first introduced in 1997 using hard surfaces, and it was only in 2002 where we saw the first study addressing friction on relatively soft surfaces using colloidal probes. So in 2020, we published a review article on frictional properties of soft materials at the nanoscale, and where we highlight the central role of FFM in the research. Now, we noticed that while many studies utilized friction force microscopy to measure friction on biologically relevant surfaces, the selected surfaces, and especially the AFM probe had mechanical properties that were quite different from what you usually find in biological surfaces. So while hard surfaces often serve as a reference, it's important to emphasize the unique characteristics of soft surfaces. For example, their deformability, which plays a significant role in the frictional behavior. So by using hard surfaces, you sometimes overlook the importance of deformability in friction in those systems. So before I continue with some case studies, I would like a bit to touch upon calibration for friction force microscopy. So a widely used method was developed by Ogletree, Karpik, Salmeron, and others and uses a wedge to calculate the lateral spring constant. So basically, you run the cantilever on top of that wedge, and you get the forces there, and you calibrate it. So while you can find commercially available wedges that you can use them to calibrate sharp tips, it's not that easy to do it with the colloidal probes because they are much larger. So there's another more appropriate technique that I mostly use in my experiments that uses beam mechanics. So this needs so what you do in this, you actually, if you know the dimensions of the cantilever, you can calculate how what are the contacts, how to calibrate it and how to get the spring constants and the lateral constant correctly. So what you do is you have to actually do first a force distance curve where you get the sensitivity of it and you measure the adhesion when you do the pull of force. And then you use other technique to calculate the spring constant. And then you combine that with cantilever dimensions and mechanical properties and calculate the spring constant on the lateral dimension and also the sensitivity of it. So once you calibrate the cantilever to know how much it bends with a specific force, you then do a friction loop where you run your cantilever forth and back on the surface. And then you can calculate how much is the friction force developed between the two surfaces. So also before moving to case studies, I would like to briefly to show, to introduce the QCMD. So QCMD is a highly sensitive technique that is used to characterize in real time adsorption on the surface. So it's using a piezoelectric material which oscillates at a resonant frequency. And when you add mass on that sensor, the frequency slightly changes. And from that difference, you calculate how much mass is absorbed. And also give information about film thickness and viscoelastic properties of the film absorbed. And it's a very useful tool to calculate, to see what's on the surface at this scale. So in our first case study, I will focus in a 2021 publication from our previous group. So the primary objective for that study was to understand how the elastic modulus was affecting frictional properties of both bare and protein-coated surfaces at the nanoscale. So the first step was to create surfaces with tunable elastic modulus that can mimic the mechanical properties of biological surfaces. So to do that, we used two commercially available silicon products that had different elastic modulus, and we mixed them in different ratios. And we prepare 5 different surfaces with 5 different Young's modulus, elastic modulus. And then by using AFM, we characterize their mechanical properties. So as we can see in the graph, there is an interesting pattern here. So as the indentation depth increases, so does the Young's modulus, and particularly in samples with higher modulus, until eventually gets a plateau and stabilizes. So this initial increase in modulus as you indent more and more on the surface was related to factors such as ordering and confinement effects at the surface, and also surface roughness. Now, at the plateau, the modulus we measured was similar to what we found using macroscale techniques. ranging from 150 kilopascal to up to 2 megapascal. So before proceeding, I would like just to show this slide because I think it's quite interesting. So a popular technique to hydrophilize PDMS is by using UV ozone or plasma treatment. However, we found that by using this one, you form a thin layer, an oxidized layer on the surface that alters the mechanical properties. So it's quite stiff. So as you see from the graph, the modulus raises quite a lot. So if you are considering using UVO for nanoscale studies, just keep that in mind that it will change the properties of the film. So moving on to our results. So friction is a system property and varies with many factors such as roughness and hydrophilicity. Now, to rule these factors out, we used AFM to image the surfaces with different modulus, and we also used contact angle measurements. Now, as you can see in the AFM images, despite having different modulus, all PDMS surfaces showed similar morphology, with an RMS roughness of about 4 nanometer for all of them, while they also had similar hydrophilicity at about 120 degrees. So we can ensure that we can rule these factors out, so they won't affect friction in what we see later. So let's now look at the friction. So initially we attached a glass particle at the end of a cantilever and we measure friction on PDMS samples in a buffer environment without any proteins. So as can be seen in the graph, friction does not have a linear dependency on the applied load, which hints a single asperity contact. So softer surfaces exhibit larger friction, and this is likely due to the increased adhesion as we see in the graph down here. So we fit our data with the GTE equation and we found the JKR regime, which indicates single asperity contact. So what happens is that as you squeeze the glass on the PDMS, this compresses out the asperities, which we also confirm with further calculations. So moving on from glass to PDMS, we prepare PDMS particles using PDMS in PVA emulsion, and then we got them and attach them at the end of the cantilever. So what we did here was using the PDMS particle. Sorry, that's the glass. So this is the glass again. So what we did is, again, we use glass on PDMS, but in this case, to simulate what happened in biological systems, we put protein solutions there. So we used negatively charged beta-lactoglobulin and also positively charged lactoferrin. So the proteins, as you expect, screen the interactions between the probe and the surface in both cases, reducing the adhesion about 100 times, as can be seen down here, as compared to buffer. And they also exhibited different behavior than previously. So in the presence of lactoferrin, the friction linearly increases with load and having a coefficient of friction of about 0.20 for all surfaces. For beta-lactoglobulin, friction initially increases slowly with load and has a coefficient of about 0.05, but beyond 30 nanonewton, the friction is increased to 0.20 for all surfaces. Now we plot the CR stress by the contact pressure, so we can rule out the effect of deformation on our data, and we observe that deformation does not affect the frictional properties of these systems. So what happens at protein coatings reduce friction and adhesion, and they steer towards a multi-asperity contact, similar to what happened at Hamilton's law at the macro scale. So having examined friction with a hard probe, we move to a softer probe, so a PDMS probe, and we measure friction between PDMS and PDMS in protein environment. So when we tried to do PDMS versus PDMS in buffer, we had very large adhesion and we couldn't continue, so I don't have this data. So as we see here, lactoferrin increases linearly with load, with a friction coefficient being independent from the modulus of the PDMS. So it's similar to all surfaces, and it's about 1, which is 5 times larger than what we observed at the same system using the glass probe. Now it can be seen also that interfacial shear stress increases linearly with increasing pressure. Now, in contrast, beta-lactoglobulin exhibits a distinct behavior from lactoferrin. So the friction force is generally lower and does not show direct correlation, a direct linear increase with load, and seems to be exponentially increasing. So the similar happens when you plot the shear stress versus contact pressure, where it's increasing exponentially. So the coefficient starts up from about 0.2, as we can see in the graph here, and rises at about 1 at higher loads. But more importantly, the coefficient of friction does show a dependency on the elastic modulus, with substrates of higher moduli exhibiting a higher friction coefficient. Now, from these findings, it becomes evident that while both proteins have different lubricating properties, their effects are modulated by the hydrophilicity and stiffness of the colloidal probe, as well as the elastic modulus of the underlying surface substrate. So to gain an insight of the surfaces and the mechanisms that are developed during nanotribology, we visualize the protein films using AFM. So the image reveal that lactoferrin forms large islands, large aggregates, which is driven by their molecular structure and charge distribution of those proteins. But you see actually that there are large surface patches that remain either bare or sparsely coated with lactoferrin. In contrast, when we see the beta-lactoglobulin, it appears to uniformly coat the surface, so that the nanoporous structure is no longer visible. So it creates a nice uniform film on the surface, coating completely the PDMS. So we also use QCMD to check a bit about the properties of the films. So we found that BLG forms a thin film, which is more rigid as compared to lactoferrin. So when we compare the data from QCMD and AFM, it's evident that while lactoferrin forms a non-uniform film, while BLG forms a uniform, they have a significant number of hydrated proteins adsorbed on the surface. So this is also consistent with the SCF field theory calculation. So what actually this does is you calculate, you get the protein, and actually you have it in a linear structure, not compacted in a 3D structure as it is in nature, and you see how far it sits from the surface when it adsorbs. And what we see here, we saw that BLG sits closer to the surface as compared to lactoferrin. So in summary, we can say, actually we can propose a lubrication mechanisms in this graph here. So as we can see, initially both proteins coat the PDMS surfaces to a different extent, and effectively screening the interaction between the two surfaces. However, once sliding begins, lactoferrin is easily removed from the contact area, that resulting in high friction, because you have like PDMS versus PDMS, which has a very high friction buffer. In contrast, BLG exhibits very strong adhesion with the PDMS and leading to reduced friction. However, as the load increases, you eventually have the frictional forces removing and dehydrating that adsorbed film, which in turn increases the friction coefficient. Notably, surfaces with a lower Young's modulus can withstand a greater normal load before the BLG or proteins can displaced from the surface, as the normal load is distributed over a larger area and resulting in lower contact pressure. So in conclusion, the dependence of Young's of friction on the Young's modulus is as a consequence of both the physical properties and the morphology of the protein film. And these characteristics are dictated by the protein's chemical nature, its affinity for the surface, and the ease with which the protein is removed from the interface. So I had one more case study, but I see that I'm running out of time here, so I will stop here, I think. I don't know, I think I need about 10 minutes for the rest. Should I go ahead or stop here?